Chapter 21, carboxylic acid derivatives. We're going to learn naming of carboxylic acid derivatives, methods of prep, and reactions of carboxylic acid derivatives. These derivatives, they actually vary from one to another by changing the group that's attached to the carbonyl. So if I look at the very first group of acid derivatives, that's acid halide, I will find that there is a halide attached to the carbonyl that makes it the acid halide. So I could have a chloride that will give me the acid chloride, bromide, acid bromide, iodide, acid iodide. We will learn how to name these compounds. Now, when it comes to anhydride, that's a second carboxylic acid derivative. You have an oxygen that's separating two carbonyl. So that's basically the moiety that's needed for a compound to be labeled anhydride. And usually what it means that there is a lack of water. So think of it as basically two carboxylic acid coming together to make an anhydride. So you're taking a hydrogen from one acid and an OH from another, and that will be the H2O. So that's why the name is anhydride, meaning loss of water. Ester, when you have an alkoxy group attached to the carbonyl, and amide, when you have an amino or a substituted amine attached to the carbonyl, since you could have a primary amide as the one you see in front of you. Secondary amide is when you have an NHR prime, and a tertiary amide is when you have no hydrogens attached to the nitrogen. And the other, or the last derivative that we're going to learn about its chemistry in this chapter is the cyano compounds, or the nitriles. These compounds or acid derivatives, they exist in a lot of structures that can be actually biological active compounds, and they may actually exist in structures that give them the character, certain character, like for example banana oil or other perfume oils that do have smell. That's due to the fact that there is an ester group. Penicillin G, you could see here that there is an amide or carboxylic acid or a thio group. These contribute to biological activity as well. Like penicillin G is one of the antibiotics that actually fight bacteria. So that's important to keep in mind, that the importance of building those moieties can contribute to an important function of a certain structure. So let's start with carboxylic acid. So we already learned how to name carboxylic acids from previous chapter. So we said the alkane becomes an alkanoic acid. So ethane, ethanoic, propane, propanoic, and so on. So that's important to keep in mind when it comes to naming an ester. Why? Because when I have an ester, and we're going to learn how to make that, basically starting with a carboxylic acid and an alcohol and presence of H+, will give me an ester. That's the Fischer esterification. We've seen that in the previous chapter, but here it is again, a method how to prepare esters. And when I name an ester, I always have to start with the alkyl group that's attached to the oxygen of the ester group. So in this case, I have a methyl carbonyl oxygen ethyl. So my ester should sound as alkyl alkanoate. Alkyl, that's the alkyl group that's attached to the oxygen. Alkanoate, that's the ester chain. So when I have this molecule, that means I have an ethyl, and this is ethanoate. So from ethanoic acid, so ethanoic acid becomes an ethanoate when it's an ester. Common name is ethyl acetate. Again, you are responsible for naming these compounds the IUPAC way. Here's another example. So we have basically the isopropyl being the alkyl group, and I have a methanoate here. So I could say isopropyl methanoate, or I could say 1-methyl ethyl methanoate, because this group, it's actually a substituent sitting on another alkyl group. So that's a methyl sitting on an ethyl. That's where the name comes from, 1-methyl ethyl methanoate. But again, I will accept naming this as isopropyl methanoate. Why is it methanoate? Because it's if I would name this as the acid, it would be methanoic acid. Here's another example. So I have a phenyl benzoate. So that would be the name of this ester. Here's another methyl, and I have a phenyl attached to carbon number 2. So that would be 2-phenyl ethanoate. So if you face trouble naming an ester, just go back to the corresponding carboxylic acid. How would I name the acid that correspond to this structure? I will have phenyl CH2 carbonyl OH. That would be 2-phenyl ethanoic acid. So the name of the ester will be methyl 2-phenyl ethanoate. Here's some more examples. So I have a benzyl group that's sitting on the oxygen side. So that will be my alkyl. And the alkanoate will be basically propanoate. But this propanoate in carbon number 2, there is a methyl. So the name becomes benzyl 2-methyl propanoate. We named, if we have a cyclopentane with a carboxylic acid moiety attached to it, we named that as a cyclopentane carboxylic acid. Same thing here. If I would have a cyclopentane with an ester group attached, that would be named as basically carboxylate. So methyl would be the alkyl group, and this would be cyclopentane carboxylate. There's the last one. We have basically the methanoate again, and I have a cyclohexyl being the alkyl group. So cyclohexyl methanoate. So it's a very easy task. The moment you have an ester, just identify the R group that's attached to the oxygen and name the chain of the ester as it sounds, alkanoate. Lactones. Lactones are cyclic esters. So in order for me to make a cyclic ester, I'm going to need an intramolecular reaction between an alcohol and a carboxylic acid. And this is important to keep in mind. Why? Because naming the lactone will depend on how we name that hydroxy carboxylic acid. So if I look at this structure, I have basically an OH on one end and a carboxylic acid on the other. In presence of an H+, that should remind me of the reaction of an alcohol with a carboxylic acid. We just seen that. Alcohol with a carboxylic acid, in presence of an H+, that's Fischer esterification. So I end up making an ester out of it. What if the alcohol and the carboxylic acid are within the same compound, within the same structure? So I could have basically that esterification happen without having a second molecule. So this OH will end up attacking the carbonyl once it gets protonated, and it's going to go through the same process how we do the esterification. And that gives me the lactone. So a cyclic ester will always be named lactone. Now, how do we name it? I will need to go back to the hydroxyl carboxylic acid and name that. The name would be 1, 2, 3, 4. So that's a 4-hydroxy butanoic acid. 4-hydroxy butanoic acid. Naming its lactone would be 4-hydroxy butanoic acid lactone. So all what I do here is just add a word lactone after how I name the corresponding hydroxy acid. So that's important to keep in mind. Here's another example. I have basically the 1, 2, 3, 4, 5. So that's 5-hydroxy pentanoic acid. But because it's a lactone, then it's 5-hydroxy pentanoic acid lactone. Here's another. So I have a 2-methyl and 2-methyl, and I have basically the 1, 2, 3, 4, 5. So that's basically the pentanoic acid, but it has a methyl group sitting on carbon number 2, and I have the hydroxy sitting on carbon number 4. So that would be named 4-hydroxy 2-methyl pentanoic acid. But since I have the lactone version, then it's a lactone parent name. So that's important to keep in mind. We already learned how to do the alpha, beta, gamma, even though it's a common system naming or common naming system. It's good to know what alpha, beta, gamma means. It all basically a reference to the carbonyl. The further away it is, that's how it gets its labeling. So alpha would be the carbon next to the carbonyl, beta would be the second carbon away, gamma would be the third. Amides. How do I name amides? First of all, we need to keep in mind that one of the ways how to make an amide is actually to mix a carboxylic acid with an amine. We learned that in a previous chapter. So mixing them at room temp, it will be just an acid-base chemistry. So I will end up making an ammonium salt. In order for it to be pushed to make an amide, I'm going to need actually heat. And the heat will make the amide structure at the end. So the way how we recognize amides in IR spectrum is by finding the two peaks around the 1700. That these two spikes around the 1700, it tells us that there's actually an amide in the structure. So due to the fact that the carbonyl with the nitrogen attached, it does have a resonance where the lone pair moves in to make a pi bond and break up the double bond to make a negative charge on the oxygen. I still deal with a major contributor, that's the neutral one, but I cannot ignore there is the imine structure that does contribute to the amide structure. So this phenomena is recognized clearly on the IR spectrum. How do I name amides? The alkane becomes alkane amide. So it should sound as basically, if I have an amide structure, if I have an alkyl group attached to the nitrogen, well, let's start with this one. This one, for example, I have a cyclopentane. If it would have been an acid, it would be named cyclopentane carboxylic acid. But if I have the amide, it would be cyclopentane carboxyamide. So that's important to keep in mind. If I would have no ethyl group here, then it would be named basically ethanamide. Ethanamide, because of the fact that there is a CH3 carbonyl, that's an ethane corresponding amide, and you have the amide group, which is the NH2 attached to it. But what if I have a substituent sitting on the nitrogen? That should remind me of how I named the ester. I look at the R group that's attached to the oxygen. The amide, I look at the R group attached to the nitrogen. So how would I name this? This would be N-ethyl, indicating that the ethyl group is sitting on the nitrogen, and the parent name be ethanamide. So the common name would be acetamide, as ethanoic acid is corresponding to acetic acid. So the amide would be acetamide. Here's another example. So I have basically the nitrogen attached to two methyl groups. So that's an N-dimethyl methanamide, because I have a one carbon attached to the nitrogen. That's the carbonyl. Here's another example where I have the N-ethyl, and I have two methyl groups, one on the nitrogen and one on the chain of the 3 carbon. That's a propanamide. So I will name them as basically N-ethyl and 2-dimethyl propanamide. So the propane would be the parent name, and the substituents, whether it's sitting on the nitrogen or the chain itself, will be basically prior to the name. Here's another example. I have basically 2 methyl groups sitting on the nitrogen, so that's an N-dimethyl cyclopropane carboxamide. So carboxylic acid becomes a carboxamide. So this is another. So I have an aniline, and attached to it I have an acetyl group. So the acetanolide is referring to basically an acetyl group sitting on the aniline, and because it's an amide group now, it's the structure becomes an acetanolide. You may say it as acetanolide, that's fine too, but the common way of saying it is acetanolide. So we can see here there is a primary amide version. The secondary amide is when you have at least one carbon attached to the nitrogen, 2 carbons attached. That makes it a tertiary amide. Just like lactones, there are cyclic esters. There is the cyclic amides. These are called lactams. Lactones and lactams. The same chemistry we went over in regard to the lactones, having a hydroxy group attacking a carboxylic acid. Here, we're going to need an amino group attacking a carboxylic acid. So heat is required, because if I don't have heat, I may end up having just an acid-base chemistry. So I'm going to need to have heat to push the amide structure to be formed. So how would I name this? The same how I named the lactone. I go back to the hydroxy carboxylic acid, and in the case of lactam, I go back to the amino carboxylic acid. So how would I name this structure? 1, 2, 3, 4. So that's a 4-amino butanoic acid. The lactone becomes, or the lactam becomes 4-amino butanoic acid lactam. So that's all what I need to do is just to go back to the amino carboxylic acid, name that, and then insert the word lactam. Here's another. You can see here that I have basically the 1, 2, 3. So that's 3-amino propanoic acid lactam. Here's another. I have a 1, 2, 3, 4, 5, 6. So that's 6 amino hexanoic acid lactam. So that's very important to keep in mind how to go back to the amino carboxylic acid. All what you need to do is just add H2O. So OH will go to the carbonyl and H goes back to the nitrogen. So here's the last example. So I have a 1, 2, 3, 4, 5. So it's a 4 amino 2-methyl pentanoic acid lactam. If this would have been an oxygen, all what you need to do is just put a lactone instead. And of course, it becomes a hydroxy, as we've seen it earlier. Nitriles. We're going to learn some of the methods how to make a nitrile. So one of the methods is to do acid or basic hydrolysis of basically of it to give me an amide and then to give me an acid, or I could go back from the acid and make a nitrile through a same route. So I will basically insert an ammonia or an amine to make an amide, and then take that amide and go through the step of POCl3, which is considered to be a dehydrating agent, and that will take off water from the amide to give you a nitrile. We will see this method later on when we discuss methods of prep of nitriles. Now, how do we name nitriles? It will be named, and it should sound as alkane nitrile. So it's as simple as you just hear. So 1, 2, so I have an ethane nitrile. 1, 2, 3, 4, so I have a 3-bromo butane nitrile. So the carbon of the nitrile, or the cyano, is counted part of the longest chain of carbons. So that's important to keep in mind. Here's 1, 2, 3, 4, 5. So that's a 5-methoxy hexane nitrile. That's important to keep in mind, that the alkane E, it is in the name, and the nitrile will be the last, no space between the nitrile and the alkane name. It's an sp hybridized carbon and nitrogen. That's important to keep in mind. So when you draw a structure that does have a cyano, be careful not to put it in a zigzag formula. Make sure that it does actually show as a linear shape moiety, as it is 180-degree bond angle. Acid halides, that's another acid derivative. So it's one of the very reactive, actually, acid derivatives. So nucleophile, when it reacts with it, it basically attacks the carbonyl carbon, and it pushes the pi bond toward the oxygen, makes a negative, and that goes back and kick off the Cl. So it's a very common nucleophilic acyl substitution, due to the fact that the acid halide is a very reactive acid derivative. So we will actually come across ranking of acid derivatives, and we're going to see the factors that usually contribute to how we rank those acid derivatives. Now, how do we name acid halides? It should sound as alkanoyl halide. The alkane, once you have a carbonyl halide, it should sound as an alkanoyl halide. So here's an example. I have 1, 2, so that would be named ethanoyl fluoride. Here's another propanoyl chloride. Here's another 1, 2, 3, so that's a 3-bromo butanoyl bromide. Be careful not to say alkyl bromide, because alkyl bromide doesn't indicate that you have an acid halide. It indicates that you have an alkane chain and you have a halide at the end. So you have to say alkanoyl, OYL, as basically indicating that there is an acid halide. Here's another. If I would have the carboxylic acid, then it would be named cyclopentane carboxylic acid. But here, because it's an acid halide, it would be named as cyclopentane carbonyl chloride. Acid anhydrides, as I mentioned, it's basically, the name comes from losing water. It's because if you would have the anhydride mixed with water, that's one of the reactions that we're going to learn in reactions of anhydrides, you will basically hydrolyze it back to 2 carboxylic acids. So you could see clearly that one of the hydrogen will go to one end to make a first carboxylic acid, and the OH will go to the other side, which is the carbonyl, to make the second carboxylic acid. How do we name anhydrides? Well, keep in mind that the reactivity of acid anhydrides is actually less compared to acid chloride, but it's still a reactive acid derivative. It will still go through what we call nucleophilic acyl substitution. So that's important to keep in mind, that the carbonyl carbon is the one that's going to be attacked by the nucleophile, no matter what it is, as we're going to see later on in the second part. We will see how the nucleophile attacks the carbonyl carbon and then pushes the pi bond, just how we did the acid halide, towards the oxygen to make a negative charge. So you go from a trigonoplanar to a tetrahedral, and then that O- will go back and kick off the acetate or the alkanoate. So that's or the carboxylate. That carboxylate will be the leaving group. It's not going to be as good as an halide, but it's still considered a good leaving group. Naming acid anhydrides. How do we name it? Will always depend on the carbon chain, how many in there. So for example, if I have 1, 2, that means I have an ethanoic anhydride. So it should sound as basically alkanoic anhydride. What if I have 2 different ones? Well, we will see that as an example. Here's another. So I have a trifluoroethanoic anhydride. If I would have the acid, it would be trifluoroacidic. It will trifluoroethanoic acid, but since I don't have the acid, I have the anhydride, then I will change it to trifluoroethanoic anhydride. Here's another example. So I have a benzene 1,2-dicarboxylic anhydride, and here's an alkene with an anhydride attached. So that would be basically, instead of saying butane dioic anhydride, it will be named butene dioic anhydride, due to the fact that you have an alkene carbon number 2. So 1, 2, 3, 4. It's a butane dioic acid, but since I have an alkene, that's why it's a butene dioic anhydride. What if I have the anhydride unsymmetrical? Here's an example. So I have basically an oxygen of the anhydride separating an ethanoic from a methanoic. Then I will go alphabetical. The first alkanoic term of alphabet will show up first. So in this case will be ethanoic, methanoic anhydride. Ethanoic, methanoic anhydride. Here's another example. So I have an ethanoic versus propanoic. So obviously the ethanoic will go first. So trifluoroethanoic, propanoic anhydride. So once again, the alkane, when it's in the anhydride version, I will name it as alkanoic anhydride. If I have the unsymmetrical anhydride, and then I will be naming each side as alkanoic, and I will start with the alphabetical order one first. In terms of nomenclature, having multiple function groups, keep in mind the following ranking. Carboxylic acid, as it is the most oxidized moiety, will always be number 1 in naming the structure. So the acid will be the parent name. So that alkane becomes an alkanoic acid. Ester would be next. Amide would be 3rd. Nitrile will be 4th. Higher priority than aldehyde, which is higher priority than a ketone, then an alcohol, then an amine, then an alkene or alkyne. In fact, there is also the ether and then the halide. They come at the bottom of the list. So the ether and the halides have the least priority when it comes to naming an organic structure. So we will see that actually here in a minute. But let's look at this. So I have a cyano, so I have a nitrile and I have an ester. So I know the ester has a priority. So the cyano becomes a substituent. So what do I have here? I have an ethyl, and that will be the alkyl, and then ortho or 2 cyanobenzoate. So I have a benzoic acid moiety, but this, because it's an ester, now it should sound as a benzoate. How we name the ester is always by naming the alkyl group of that ester oxygen side, and then I name the chain as an alkanoate, and that's what we did here. Ethyl, benzoate, but I have a cyano group attached, so that will be basically ethyl 2-cyano or orthocyano benzoate. Here's another example. So I have a cyclohexane carboxamide, and I have an aldehyde. How would the aldehyde be named as a substituent? Formal. So 2-formyl cyclohexane carboxamide. Here's a hydroxy and a nitrile. So I know the nitrile, as it is more oxidized than an alcohol. That's why it's going to take the priority in naming the structure. So this would be 1, 2, 3, 4. So that's a butane nitrile. And I have a hydroxy sitting on carbon number 2. So that's a 2-hydroxy butane nitrile. And as I mentioned, here's the list of all the functional groups that we're going to have in this course, or what we have studied in previous course. So carboxylic acids will always be named as alkanoic acid. Esters will be alkanoate. So the alkyl group of the carboxylic acid ester first, and then alkanoate. Amides would be alkane amides. Nitriles will be alkane nitriles. Aldehydes will be named as alkanal. Ketones will be named as alkanone. Alcohols, alkanol. Amines will be alkylamine. Sometimes it's alkanamine as well. Alkenes is basically when you have a double bond, alkynes and alkanes. And the bottom of the list, ether would be named as usually alkoxy. So if there is a substituent that you have of an ether, it will be an alkoxy. And you could see here clearly that the carboxylic acid, it's a carboxy. The ester is attached to an alkoxy in the side of the carbonyl, and the rest of the groups that you see here that usually show up in these compounds, and how they would be named when they are a substituent. So the nitrile becomes a cyano, aldehydes become the formyl, ketones becomes the oxo, alcohol becomes a hydroxy, amines becomes the amino, and so on. So keep that in mind, that every single group, I need to make sure that I understand, I rank them correctly when it comes to which one gets a priority in numbering the structure. Yes, the first rule in IUPAC is always finding the longest chain of carbons. But which longest chain of carbons am I supposed to look at? Is it the one that has the carboxylic acid, or is it the one that's going to have the alcohol? Well, obviously the carboxylic acid, as it is going to be number 1 in priority. So keep that in mind. Physical properties of carboxylic acid derivatives. Usually, it depends. The trend will always depend on the strength of the intermolecular forces formed with these within these acid derivatives. So the amide always actually found to be, especially the primary amide, was found to be actually the highest in boiling point or melting point, due to the fact that it does have multiple sites to form a hydrogen bond. So if I would have a primary amide, I would expect it to be a higher in boiling point than the corresponding carboxylic acid, that a comparable number of carbons, obviously. So is not the carboxylic acid, the carboxylic amide is going to have a different intermolecular force. It's still going to be hydrogen bonding, but that hydrogen bonding, due to the fact that there is multiple sites, it makes it a little higher than the boiling point or melting point of the carboxylic acid. So that's important to keep in mind. Now, carboxylic acid will be higher than an alcohol, higher than a nitrile, higher than an ester, or the corresponding number of carbons if it's an alkane. So that's important to keep in mind. The trend always goes from primary amide to a carboxylic acid to an alcohol to a nitrile to an ester. So the alkane, obviously, due to the fact that there is no polar intermolecular force, it's a London dispersion forces that actually contributes to the low boiling or melting point of these alkane structures. Keep in mind that the multiple sites we're referring to is basically when you have an amide, you could see here clearly that the oxygen on the carbon and the nitrogen do have basically contribute to the intermolecular forces that's going to be formed with another molecule of the same. And that's why you see higher, slightly higher boiling point or melting point compared to the carboxylic acid. We have seen already the IR and NMR in previous talk, so it's not going to be any different. I mean, we should remind ourselves that the aldehyde usually have the hydrogen around 9 and 10, but the carboxylic acid will be a little higher, so it could reach 12 to 14. If I have an alkyl next to a carbonyl, that will be read in the 2 to 2.5 region. If I have an alkyl attached to an oxygen of an ester, that will be around 4 ppm. If I have it next to an alcohol, it will be around 3.5, the same as if it's attached to a nitrogen, 3 to 3.5. The last one is the alkyl group that's attached to a cyano. It will be similar to how a carbonyl attached to that CH2, and it will be actually read around the same, so 2.5. So nucleophilic acyl substitution. That's the name of the reaction. How you will go from an acid chloride to an acid anhydride to an amide to an ester to back to an acid hale. This is how these structures give basically compounds through a type of reaction that is called nucleophilic acyl substitution, because all what it requires to go from one to another is a nucleophile attacking the carbonyl carbon, kicking off the leaving group. So that's important to keep in mind. You could also call them as acyl transfer reactions, because technically you are transferring a group to be attached to the acyl group instead of the one that exists. So this is basically the description of the nucleophilic acyl substitution. So the nucleophile will always attack the carbonyl carbon. It has to have a leaving group, otherwise it will generate an alcohol, because if you have a carbonyl of a ketone, for example, and you have a nucleophile, that nucleophile is going to end up adding to the carbonyl carbon and not substituting anything. So you're going to end up having that O- not going back to become an acyl double bond O. It will become an OH once you protonate. So this tetrahedral intermediate will have that O- basically make a double bond, and that will kick off the leaving group to give you the nucleophilic acyl substitution product. This summarizes the reactivity. And it's very important to recognize that acid chloride has a halide, that's a chloride. Anhydride has the carboxylate. Ester has the alkoxy. Amide has the amino. Carboxylate has the negatively charged oxygen. What's the definition of a good leaving group? Good leaving group usually requires a couple things. One, it's supposed to be weak as a base. So when you take that ion out, which is the Cl or the acid or the carboxylate or the alkoxy or the amine, all that, look at it as the anion. So chloride versus carboxylate versus alkoxide versus the amide, which is NH2 minus, that's the amide, and versus the O minus, which becomes actually as an O2 minus. So the weaker it is as a base, the better it is as a good leaving group. So that's how we look at leaving groups and rank them. The second thing is the polarizability. So the negative charge around that leaving group to be polarized, meaning it doesn't split between two sides. Like for example, carboxylate. Carboxylate has the O minus actually splits between the two oxygens. So that makes it weaker. And the acid will become actually as a base. Actually, it makes it as a weaker base than the Cl minus. So that's important to keep in mind. So O minus, the RO minus, it doesn't have resonance, so that's why it's a stronger base than the carboxylate. NH2 minus, the reason why it's a stronger base than the alkoxide. Think of the conjugate acids. I have an alcohol which has a pK of around 16 versus ammonia which has a pK of 33. The weaker it is as an acid, the stronger the conjugate base. So that's why the NH2 minus is a stronger base than the RO minus. So the weaker it is as a base, the better it is as a leaving group. And that contributes to the reactivity. And that's why acid chlorides will be the most reactive acid derivatives. What would be next? Anhydride. What would be next? Esters. And then the amides, and then the carboxylate. So nitrile is not fair to put it in here because the nitrile doesn't have a leaving group. It's a cyano group. So we're not going to be basically doing acyl substitution. So it's going to be more of an addition reaction, as we're going to see examples of those later on. So the common question to be asked, rank the following acid derivatives. Always rank them in the way that acid chloride will be first. Next would be the anhydride, followed by the ester, amides, and then the carboxylate. That's how we usually rank them. And that's based on the leaving group that's attached to those structures. This slide shows basically the interconversion between those acid derivatives. And you can see here clearly that there is always a way to go from one to another. So the acid chloride, there is many ways how it actually can generate other structures. So we could see here that the acid chloride could be made from others, or could be actually leading to others. So anhydrides, the same thing, esters, amides, carboxylic. So these are basically acid derivatives. They are, in this chapter, you will find them in reactions that are repeated. They could be basically in a reaction where it's a method of prep for it, or in another slide, you will see basically a reactant to lead to another structure. So that's important to keep in mind, that we're going to be going over a lot of reactions in this chapter, but the good thing that a lot of those reactions are repeated. So in one section, we will be looking at it as a method of prep. In another section, we'll see it as a reaction of that functional group. And this is the first part that will be discussed, actually, that's been discussed in this chapter. The following part, we will be discussing reactions of those acid derivatives. So every single group of acid derivatives, we will look at the method of prep and reactions of that acid derivative leading to other useful compounds.